Mm-hmm. Ouch. Ooh. Okay, got to be careful with that. All right. Yep. For debugging B, the first thing I would do is to look into Arduino, make sure that you have all the reference material handy. So I would put all the bookmarks on a thumb drive, so that you have all the reference material like available right away. You also want to understand the circuitry, like common circuitry for Arduino interfacing, like how do you interpret whether a button is pushed, how do you control a servo motor, all the typical stuff that people use Arduino for. So you want to make sure that you understand all of that stuff. The interesting thing about debugging B is it's not really just about the software. It's not about just about the programming, but it's also about the wiring of the circuitry and also the design of the circuitry. So you need a whole team of people. You need um, definitely software. You also need electronics and possibly even mechanical expertise in the team. So it does resemble product design, a lot, because in product design, it's not really just the software. It's also the circuitry and how the product itself behave. Yep. So I would definitely start with the Arduino documentation, but also focus on the sample circuits that you can use an Arduino for. Like how to light up an LED, how to read back feedback from a optical sensor, how to control a servo motor. Those are very, very typical applications of an Arduino, so I would definitely look into those. All right, well, let's go ahead and get started with today's class. And because some people may not be showing up, I'm just going to talk about something that I did over the weekend. Well, not this is not over the weekend. This is something that I did before the weekend. I did something to the assembler, so now it has a added ability, which is good. Okay, I hope it's not going to break anything in the past. I don't think so. But I added the ability to parse postfix notations to the assembler. So now what you can the use of symbols can now be a lot more flexible compared to the previous version of the assembler. It's still a spreadsheet, it's still a Google spreadsheet, but I added some features to the Google spreadsheet. I can show you guys that a little bit later. All right, so we'll go ahead and first talk about what is posted or postfix. So postfix notation, as opposed to infix notation, is a way to specify an expression where the operator is specified after the operands. Okay, so in this case, okay, let me zoom in a little bit so we can see the expression itself better. So in this case, we have a fairly typical, example of an expression: x plus y, the whole thing, times z, and that becomes the numerator. And then we have 2 plus w being the denominator. So it's basically a division. It's just written as a fraction. Okay. So in postfix notation, what we do is we specify the numbers that we want to operate on, and then the operation. Okay. So in this case, x plus y becomes x y plus, because it is x, y means, okay, what are we operating on? And then the plus says, oh, we want to add those two values. So when you have x plus y, the whole thing, times z, then xy plus will give you one side of the multiplication, z gives you the other side of the multiplication, and then the multiplication symbol simply says, oh, those other two things that we have, do a multiplication. Okay? And then on the denominator side, we have 2 plus w as an infix notation. So as a postfix notation, it becomes 2w, which specify the values that we need to operate on. And then the plus, which means, oh, what do we want to do with those two values again? We want to add those. Okay? So the whole expression here becomes xy plus to handle the x plus y, z times, which handles the z multiplied to the sum of x and y. That becomes the numerator. 2w plus becomes the denominator. And then at that point, I would have both the numerator and the denominator. And then the slash simply means, of the two things remaining, I want to do a division. Okay? So is that general idea okay or not? more or less. Okay. So mechanically, the pseudocode of parsing infix notation is kind of like this. You initialize what we call an operand or value stack to empty, and then you simply go through a while expression. So you say while the expression is not empty, do the following. So in this case, expression is a list of items or an array in a scripting language. Shift is basically removing the first item out of an array or out of the list, and then the list itself is now one element fewer than before. Okay, so I'm just removing the first element of expression and put it into symbol, which is kind of like a local variable. If symbol is an operator, which means if it is plus, minus, multiply, divide, mod, and stuff like that, I would pop a number of operands from the stack based on the symbol. So most of the time we pop 2, because addition needs 2, subtraction needs 2, multiplication needs 2, division needs 2, modulus needs 2. Very few, very occasionally we will pop 1, like changing the sign only takes 1. The ternary operator would take 3, and so on. So we pop a number of operands from the stack, usually just 2. We perform the operation, and then whatever the result is, we push it back on the stack. So that is the key. Okay, after you perform the operation, you push the result of the operation back on the stack. So typically what happens is you pop 2, perform the operation, you push one thing back on the stack. The else is corresponding to what if the symbol is not an operator. I forgot here, I should have put the else push it on the stack. So any value, you just push it on the stack. Okay, I kind of rushed through this and forgot to specify else push the symbol on the stack, and then end while. So as long as you still have anything in the expression, it would try to keep parsing. So this doesn't check for error. In other words, if your operation requires 2 operands but the stack is already empty, it doesn't generate an error and go like, oh, there's nothing on the stack to operate on. Okay, so the error checking is not included in this logic. But you can kind of see that this logic is relatively simple to specify because it doesn't need a whole lot of parsing. It doesn't need okay, so I'm trying to think of the correct term to use here. So in computation theory, okay, in the Turing notation, the parser that you need for postfix notation doesn't really need so much of a stack. Okay, the parsing part does not. Okay, the processing part does. But it's very easy to process. You don't need recursion at all to do this. But if you want to deal with infix notation, which is what we are used to, you kind of need a recursion, okay, because you need to kind of keep track of things and how to, and then operator priority becomes an issue as well with infix notation. With postfix notation, there's never a problem with operator priority. They all have, quote unquote, the same priority. You don't need parentheses either, okay? So in many ways, postfix notations are very easy to parse. So here is an example of applications where the postfix expressions are actually used in a commercial way, okay? Because you might think, oh, TAC, this is your toy processor. Of course, you can use anything you see fit, in this particular scheme. But postfix notation is not something that I use, okay? In the 80s, okay, and probably into the early 90s too, HP scientific calculators and financial calculators use postfix notation. They call it RPN, or reversed Polish notation. If you ask anyone who's about my age, okay, who was an engineer, or even older, okay, people in their 60s, 70s probably got exposed to those calculators as well. But even today, we still use postfix notations in something that you probably will recognize. PostScript is a printer language, quote unquote printer language. It's not really limited only to printers. It's basically just a text language to describe what to draw on a rasterized device. So a laser printer can be seen as a rasterized device. It's just a really, really high resolution rasterized device. Your screen can be seen as a rasterized device. So PostScript, okay, is based on, guess what? Postfix. That's what the post comes from. The same company, Adobe, who came up with the standard of PostScript also came up with PDF. PDF stands for what? Exactly, portable document format. But guess what? Adobe is not reinventing the wheel over and over again. So PDF is actually based on PostScript. So you can actually use PDF viewers that can look into the actual code in the inside, and then you will see postfix notations like the ones that I just illustrated. So they would use that to calculate like the radius of a circle, where to draw the text, and locations of, how, where you want to draw what on a piece of paper, which is kind of interesting. So postfix expressions is not something that I just invented, okay? It is actually commonly used. It's just that for the end users, it is not, we typically do not get exposed to these things because we don't have to. So are there any questions about postfix expressions? It's a matter of getting used to. Yeah, go ahead.
So what in the actual processor changed that way you use postfix notation? You said.
So that's the rest of the module. Yeah, we are about close to one half done. Okay, so postfix in the TTP ASM in the assembler. Okay, this is as of today, which means I can probably add more features in the future, not this semester, but in the future. So you can use it as immediate value. In other words, if you have a label L1 that is designating the address of this byte here, and you have an L2 that is the label of whatever is after this. So when you look at the difference between L2 and L1, that becomes the number of bytes in between, right? Okay. So in the past, if you want to load A with the length of this thing, which is 3 bytes, you can either specify just 3 here, okay? Well, you can only specify 3 here because you could not do calculations. But now it can. So now you can have L1, which is this label, which is the address of this byte here, L2, which is the address of whatever byte is following here, and then you do a subtraction. So that becomes L1 minus L2 in infix notation, which is going to be -3. It's not 3, it is -3, because L1 is the one that has an earlier or lower address, and L2 is the one that has the higher address. Is that okay? So this can come in handy if you need to compute the offset between 2 labels. You can also use postfix notation for defining custom labels. So in the past, you can only have a label definition like L1, L2, colon, but here you can also define the actual value of a label. Yes?
So I was used to doing something along the lines of x subtract xy, right? Instead of to do the subtraction. Could we use the subtract symbol the whole time, or was I just doing
subtract?
It that way? Like say I have 2 registers A and B. I'm trying to do a subtraction A minus B in the taxoid processor. I would say sub space A comma B, right?
Mm-hmm.
So could I just use
Nope. This is compile time only. So that means it can only deal with constants or things that are resolvable at assemble time. What you're talking about is something that can only be resolvable at runtime because the content or the value of a register cannot be determined at assemble/compile time.
Oh, okay.
Yeah.
Okay.
But that was a good question. So now we can have something like this. The 1 is just a line number, so ignore the 1. So L3 colon without a 5 is the typical way that we define labels before. So now we can actually say, oh, we want L3 to be 5. Okay, so instead of the current address, we can say specifically, what is the expression that defines the value of a particular label. Is that okay? Kind of like a const in C and C++. Okay, which allows you to define the symbolic name of constants, which can come in handy for a few applications. But we'll kind of move forward and talk about, in this case, if L3 is actually defined to be 5, then we can define L4 to be relative to L3 because we can refer to a label in the calculation of the definition of another label. So in this case, L4 as a label is defined to be whatever L3 is plus 2. But it's using the postfix notation, and that's why it reads a little bit funny, because it's L3 2 plus. But it really means L3 plus 2 in infix notation. Is that okay? All right. So that gives you the ability to compute an actual label definition using other labels. Yes, go ahead.
Normally, when we use JUMPI jump to L4, we are going
Well, it depends on what you're using the label for. So with this extension, you can use a label not only as a label to jump to, but you can just use a label as if it is a symbolic name. And later on, I have some examples of how you can use it. Okay. So now, the assembler does detect circular references. So if you define L5 based on L6 and you define L6 based on L5, the assembler actually figures out that this is a circular reference, and it would just stop and say, okay, this is a circular reference. It cannot be resolved. Okay. So there's one more thing. There's one more feature in the assembler. It's called the dot. Simply called the dot. The dot, which is a period, you just type the period in your program, it refers to the current address. So it would go like, okay, why do we need a dot? I'm hoping by now you guys are familiar with this chunk of code. Yes? Hopefully? All right. Because this is not going to be in the test, because in the test I'm not going to give you guys code related to subroutines. I think that's what I said, right, in class. So this is going to be something in the final exam. But by now, I'm hoping people recognize this code. This is how we call a subroutine, okay? We figure out where we need to return to, push it on the stack, and then we continue execution in the subroutine. So fairly typical code. And then in the comments here, I wrote down the number of bytes that each mnemonic is going to take up. The LDI mnemonic takes up 2 bytes. 1 byte for the opcode itself, LDIA, and then the other byte for the constant that we specify to put into register A. So it takes up 2 bytes. Same thing for JMPI, takes up 2 bytes. Decrement D takes up only 1 byte. STDA only takes up 1 byte. So altogether, we need 6 bytes to get this done. 2 plus 1 plus 1 plus 2 are 6 bytes. Okay? But the use of a label definition sometimes is cumbersome, because if you define this label, using a different name, and then you refer to another label that is already defined, the assembler cannot help you. The assembler cannot associate this label should be the same as this label here. As long as this label is defined somewhere in the program, the assembler would not complain. Okay? So the alternative of writing this code with the dot notation is this program here. Same for mnemonics, but without any label definition. So in this case, the dot is basically referring to the address of the first byte of the LDI instruction. So if you add 6 to the first byte of the LDI instruction, then it becomes the address of whatever is after the JMPI instruction. So you can calculate the return address based on your current address without the use of any labels in this case. So it's not foolproof, okay? It is not foolproof because this 6 here, you can mistype it as 5, right? So then it will get a wrong address calculated. But you can always refer to this as a symbolic name. So you can always call this 6, predefine a label called LEN call, okay, length of call, LEN call. So now you can refer to that label, instead of the literal constant 6. Then it becomes much less likely that you can have a typo and not be able to catch it. Is that okay? So this paves the road to even more feature in the future, because we can probably implement the concept called a macro in the future. Probably not in this semester, but in the next semester, perhaps we can have macros. All right, so section 4 talks about some practical use that you might find useful even in this semester. So instead of keeping track of where's the return address, where's the first parameter, the second parameter, and the third parameter on the stack, we can now use symbolic names to do that. So return address is defined as 0. In other words, every time you refer to return address, it is the same thing as referring to 0. It's the same thing as spelling out 0 by itself. Okay? But every time you use param1, then it becomes whatever the return address is plus 1, which is just 1. What about param2? It's param a plus 1, which is 2. And then param c is param b plus 1, which means it's 3, right? Okay? So this way, it allows you to refer to the symbolic names in your program. So if you need to calculate the address of parameter b, instead of going through your mind to figure out, okay, how many bytes is parameter b away from where the stack pointer is pointing to, assuming the stack pointer is still pointing to the return address, now you can use just symbolic names and do the calculation. You basically put param b, which is really just 2, into a local variable, into a register c, and then you add the stack pointer d to register c, so then c becomes the address of the parameter. It's a shorthand, okay, but that makes use of symbolic names, but it can be very handy because of that. So this is the new feature that I have added to the assembler. It's not going to make any difference for your current material for the test, but in the final exam, this can come in really handy because you can now refer to symbolic names, when you don't have to use constants. You don't have to keep track of the constants in your head all the time. So do we have any questions about this discussion? Any questions about the conversion between infix notation, like x plus y, to the postfix notation? No questions? Nobody's planning to do anything with this feature? Because I'm going to use this feature myself. So you might want to know how to do the conversion. Okay, so the best way to look for how to convert between infix to postfix notation is just to look up infix to postfix. I mean, I don't even have to finish typing the whole thing. Google just read my mind. There we go. So you have somebody else, writing the notes of how to do the conversion. I mean, there are probably just calculators you can also type in, and it will do the conversion for you. So let me see. Okay, well, here's a conversion from YouTube, and YouTube. So there are plenty of material online to teach you how to do the conversion. I don't even remember how I learned how to use postfix notation. I think it was out of necessity because I was, well, this relates back to programming contest, which the debugging bee really is. I won a HP calculator in one of the programming competitions. So I was looking at the calculator and go like, but how do I use this? This is not like a Casio calculator, which I was really, really familiar with. So I go like, okay, try some infix notation. Doesn't work at all. And then I read the manual and go like, oh, it only takes RPN, reversed Polish notation. So I think that's how I learned reversed Polish notation. Yep.
Actually, I learned it in using the binary tree.
Okay.
Where you have the leaves being the
Oh, traversing in a different way. So instead of using a infix traversal order, you use a postfix traversal order.
any order.
That's it. Thank you. Okay, so we'll use that to explain it. Okay. If anyone has any questions about the exam or anything like that, please go ahead and ask those questions, because otherwise I'm just gonna. Huh? I know. I know. Well, to use that password, you need to have access to my device first, right? It's not like, that's going to be a password I can use for Canvas or my email, okay?
Is it a house?
Hmm?
Your house?
No, 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 with my house, you have to get past my cats first. I got 2 cats. Yeah, but they're too cute. So any, potential burglar would just be stuck at the door playing with the cats. It's like, oh, kitty, come on, come on. They're just too cute. I should leave a note to any potential burglar. Cat food is in the fridge. and cat toys are in the cabinet. All right, there we go. Okay, so what I want to do is to show you, how to convert from infix notation to postfix notation. Okay, so that's what this slide is going to be about. Okay, I'm going to use the same example as in my notes. So what I'll do is I am just going to copy from my module, which I think is this one here. Yep. So I'll do some copying first, and then I'll show it on the tablet. So give me a moment here. There we go. So onto the tablet. Okay, so this is the expression we want to convert into postfix notation. So I'm going to use a tree as an intermediate representation, because a tree can be used to represent both. Okay, so which one we see depends only on how we walk around the tree. It's called a traversal. Okay, if you don't have any 430 exposure yet, this is like a really quick, introduction to what a tree is and why a tree is useful in general in computer science. Okay, so if you look at a tree, the top one, or the root, is the last operation, which in this case is a division. A division requires 2 things. It needs a dividend and also a divisor. The dividend refers to the numerator in this case, but the numerator itself is a product. So we have a multiplication here. A multiplication requires 2 operands. Pretty sure they got formal names, but I don't remember those formal names. In this case, the first one is a sum, but the second one is just z all by itself. The sum also has 2 operands. In this case, it is x, y, like so. The divisor, which is on the right-hand side of the division branch, is 2 plus w. So it is a sum. It is the sum of 2 and w. There we go. So do we have any questions about how this tree was constructed? The top level is the last operation. The second level are the second to last operation, and so on. And then when we look at the leaves, okay, when we look at things that do not expand any further, those are individual values. X is a value, y is a value, w is a value, 2 is also just a value. So are we doing okay with this one? Okay. So the conversion from a tree, okay, so first of all, do we understand how to convert from any expression into its tree representation? For the most part? Yes? No? Maybe? Okay. So now the question is, how do we walk this tree in order to come up with the postfix notation? It is what we call a postfix, traversal. So a postfix traversal is also called a depth-first traversal, which means we go as far as we can, and when we cannot go any further, then we do something and then we back up. Okay? So we don't do anything when we get down, but when we get back up, we actually do things. Okay? So I'm going to use a different color pen here to indicate the order of traversal. So we start with the root. This is 1. And then we want to go as far as we can go on one particular branch. In this case, we're always going as far as we can on the left branch, if there's a left branch. So we go to here. Okay, I see we can still continue to go left, right? So we go here, And then finally, we end up here. And then we say, oh, we can't go any further. Okay, if we cannot go any further, then we say, okay, spit it out. Fine, x. Okay, so x is spit out because of step 4. Then we go back up a little bit. Okay, we go back to here. And then we say, can we go deeper on the other side? Do we have any other branches that we can go further deeper into? And go like, yep, we can. So now we go to y, and then we ask the same question, can we go to the left or the right branch? Can we go any further? The answer is no. And every time when you say we cannot go any further, then you spit out the symbol that you are on with that particular node. Okay? So after 6, we get back to the plus symbol, and then we ask the same question again. Can we go any further down, at this point? The answer is no, because we have already explored the left branch, which is x. We have already explored the right branch, which is y. So right now, there's nothing else for me to do with the plus. Well, guess what? That triggers the same rule, spit out that symbol. So now, at step 7, we spit out the plus symbol. Okay, and then where do we go next? What do you think? We go back up to the multiplication symbol, right? So we go to 8 here, and then we ask the question, can we go down on any one of the branches? The left branch is already done, but the right branch we have not explored yet. So now in step 9, we go to z, and then we ask the question, is there anything below z? Nope. Okay, well, we just spit it out. So at step 9, we spit out the symbol z. And then where do we go next? Go back up to the multiplication, which is step 10 in this case. And then what do we do? What question do we ask? Can we go any further down?
I like the question when I learned it. It was, is this the last time I'm going to visit it?
But you can only know that once you know that there are no other branches that you can explore. You have already explored every single branch. Okay, but at step 10, we do not have any more branches to explore because the 2 branches have been explored already. So when there's nothing else I can do with a particular node, if I cannot go further down anymore, then we spit out the symbol. So now we spit out the multiplication symbol. So at step 10, we spit out multiplication. And then at step 11, we get back to the division symbol. Because when there's nothing to do, you spit out the symbol and then you go back up. But then we look at this and go like, but the entire right branch here from the root has not explored yet, has not been explored. So we go down here. So step 12 is the plus. And then the plus says, oh, we got stuff to explore. Sure. Let's go to the left one first. So we go to 2. So now we are at step 13. So at step 13, we spit out the 2. And then we back up to the plus, okay, which is now step 14. And then we ask the question, do we have anything else to explore with this particular plus? Yep, the right-hand side has not been explored yet. So now we go to the W, which is step 15. So at step 15, we spit out the symbol W. And then at step 16, we get back up to the plus, but this time there's nothing else for me to explore with the plus. So we spit out the symbol plus. And then we get back up to the division symbol at step 17. And of course, at this point, we have already explored the left and also the right branches of the division. So the division itself also has nothing to do. So at step 17, we spit out the division symbol. So thank you for mentioning the traversal of a tree, because that's one way to convert any infix notation. As long as you know how to convert an infix notation into a tree, you can now convert the tree into postfix notation. Yep.
Using this tree, you could display it both in infix and postfix, right? By using the same structure.
Yep. And prefix too.
Yeah.
Yep. And you can also generate prefix notation. So generating prefix notation means at any node, you spit out the node itself first. And then you spit out whatever is after the node. So that becomes a prefix notation. If you program in Lisp, then you would know prefix notation. So prefix, infix, and postfix notations, those are actually all used in various programming languages. So are there any questions? This is a great way to explain it. So thank you again for remembering, oh, we can use it as a tree. Oh, right. Yep, we can do it. Is that okay? All right. Cool. But then the question is, does the spreadsheet on Google have any reverse Polish notation parser? Because it seems like this whole thing hinges on the parsing of postfix notation. Has anyone read the code with the assembler itself? No. No one has the time to do it. I think next time we should have a debugging bee question on the assembler. Yep. Yep. Now I haven't really tried out the new assembler, after the change on this computer, so I don't really know how much it's going to impact the processing or the speed of the processing. Maybe faster, maybe slower. I just don't know yet. I think it should be slightly faster, but I could be wrong. We'll see. Okay. Yeah, I think it's slower. Nope, it's about the same as before, I think. All right. Oh, it's still working. Now it's done. Okay, so for those of you who are curious, I wrote a Google script to actually do the parsing. Remember that pseudocode? Okay, let me remind you which pseudocode we are talking about here. Right here. So this pseudocode, okay, so you can actually find this pseudocode in rpn dot. So rpn dot is basically that pseudocode. Sequence is the expression itself. It is a list. So as long as the list is non-empty, I would do this. This element is basically symbol, and we use a shift operation, to extract the first element out of the list, and then make the list itself, one fewer, and then we just compare it to plus. If it's a plus, it's hold on a second. No, that one is right. Okay. I'm just making sure that I'm looking at the correct one. Okay, getting back to the parsing. Okay, there we go. So getting back to the parsing, if the symbol is a plus, then I say, is my stack at least have 2 items? If it does have 2 items, then I pop the 2 items, perform the actual addition, and then we push the result of the addition, the sum, back on the stack. If it only has 1, then we'll consider it as a unary plus, which is okay. We just kind of leave it alone. Otherwise, we report an error message. And if it's a subtraction, kind of the same thing. We extract the 2 operands. The first one is the subtrahend, the second one is the minuend. And then we push the difference between the 2. And then if it's multiplication, then we also just do a, what is that? Oh, that's a multiplication. So we pop the 2, and then we immediately perform a multiplication, and then we push the product back on. If the number of operands left on the stack is less than 2, then we just report an error. So that's basically the same code that we saw earlier, except this one is really kind of fleshed out. This also shows you that JavaScript is really quite useful. This is all JavaScript. And you can basically use JavaScript to extend the functionality of any Google app. So you can do it in Google Document, okay, with word processing. You can use it in Google Spreadsheet, which is what we are seeing right now, the presentations, and so on and so forth. So if you have spare time to learn a new programming language, JavaScript should be on your list. Okay, may not be top on the list. Okay, depending on what else you have to consider. Yep.
So just to clarify, when you're programming, your pop and push functions have priority over arithmetic operations.
Yes.
Or does it have
So the
precedence?
yes, because the dot operation has precedence over every other operator.
Same as C.
Yep. Yeah, JavaScript borrows its syntax from C and C++, so it borrows the same operator priority from C and C++. Yep. So if anyone is interested in the implementation, this is how it's done. And the symbol resolution, oh, dang it, I should have shown you that too. So the symbol resolution, in other words, if you have a whole bunch of dependency between the symbol definitions, that is resolved in a function called resolve symbol RPN, which is then called from a resolve reference. So this is the function, or this is the code that will figure out, oh, this symbol depends on that one depends on this one depends on that one depends on all three of those. So it will figure out that dependency and then step by step resolve the actual values of each label as it goes through the steps. And will detect circular references. So if it goes through 2 iterations and the number of symbols resolved is the same, still unresolved, then it knows that we have a circular reference. So that's it's kind of interesting for those of you who are interested in this sort of thing. Yep.
In the Google Script Editor,
Uh-huh.
at the top, it looks like you can only like run one function at a time,
Uh-huh.
but you have all the other functions calling each other, right? Is that how you make it work?
Correct. So it has to be triggered by at least one of those. So you can associate these functions to callbacks or events. So basically, anytime a document opens, you can make it happen. But the way I trigger this is this. So if you go back to the spreadsheet, go to the Assemble tab. So there are some major changes in terms of how this thing works. So when you go back to the Assemble tab, let me see which column we're talking about here. Nope, that's just a symbol. None of these actually depends on it. So all the labeled references doesn't do a single thing. So let me just add one line of code here. Okay, I'll just do a LDI A with param A. Okay, let's make it plus param B. Okay, there we go. Okay, so when you go to the Assemble tab, this, decimal to hexadecimal parameter 1 expects new number value, but it's not. Oh. All right, well, apparently I didn't quite get the entire thing done yet. It was close. Okay, so it's 2. Okay, so this is where it refers to RPN expression dot. This is the actual trigger of the calculation, but it depends on symtab $1, and that really is the one that triggers the calculation and resolves all the symbols. So if you go to that last tab here, see this huge mess here? This is the actual symbol table. This is the symbol table where it says, x_a is defined on line 0. It has no further references because we have resolved all the references. The RPN is just 0. It's defined as 0. That's what it means. Address, there's no error, so everything is good here. So this is what we call JSON, JSON, otherwise known as JavaScript Object Notation. So it allows you to take a whole data structure, in this case it is a symbol table, and convert it into text form, which makes it very handy because now you can say, oh, this one cell is actually a big, huge object because it's just text. You can also transmit it using HTTP, using any type of protocol. So it's a really useful feature in JavaScript is to convert an object into a JSON or JavaScript object notation. So this is a symbol table that the other cells refer to. So unfortunately, I forgot something here, and it is complaining about it cannot do the conversion. So it's complaining parameter 1 is expecting number value, but unresolved reference is a text, cannot be, I guess it's this one. Unresolved reference, why would it be? Oh, I know why. Yes. I kept saying, this entire lecture was about postfix notation, and guess what I used? Uh-huh. Okay. A little bit absent-minded. There we go. All right. So we'll check this out. It's calculating. Yep, it worked. Because I was wondering, why is it unresolved? Unresolved reference is actually the error message. It came straight back from the assembler because it's considering param A plus param B as one entire symbol, and well, we don't have a symbol called param A plus param B, so that's why it choked. So next thing I need to do is to make a infix to postfix converter. It's going to be difficult because infix notation is actually difficult to parse. You need what we call a look ahead mechanism. In other words, you need to look ahead of a symbol by one symbol to know where you need to do next. So it's not as easy, nearly as easy as postfix notation. And that's why I chose postfix notation, because it's easy to parse. It's just that I have to remember, we're dealing with postfix notation and not infix notation. There we go. So any other questions? No other questions? The one thing this is going to buy us is now we can talk about records or structures in C and C++. I was never able to talk about that topic in this class because I didn't have the ability to express a symbol relative to another symbol. But now that we have this ability, we are ready to go. We can now talk about it. I can extend the class content just a little bit to also include structures. Okay? All right, so before we talk about how to convert between structures and assembly code, we'll just go ahead and take a look at some basic code in C and C++ that involves the use of a structure. Okay? So this part should be a review. Okay? So in C and C++, you can define a structure, and you can define the name of a structure, kind of like a class name. You can call that, we'll just call it X. Okay? So inside X, we can have, and in this case, I'll just use, unsigned 8-bit integers. Okay? So we can have unsigned 8-bit integer A, followed by unsigned 8-bit integer, and this time is a pointer, to another unsigned 8-bit integer, and then we can have another unsigned 8-bit integer B, okay? And we'll call this, a structure here. So it's basically the same thing as a class, except all the members are by default public. So for those of you who know how to define a class in C++, it's the same thing as a class, except everything is by default public. And in C, you cannot put a method inside the definition of a structure. It can only have properties members, okay? So this is kind of like a very restricted version of a class. Are we doing okay so far with that? Okay. So now the question is, okay, This is just sample code. It may not compile. Okay, it doesn't really matter. So if I look at f here as a function, and I say struct x, we'll give it a name here, var1. Okay, so var1 is a struct x. It is on the stack because it's a local variable. So now the question is, where do you think is var1 dot a as opposed to where is the address of var1 dot ptr as opposed to the address of var1 dot b? What do you think?
Towards the bottom of the stack, and B is at the top. Yes.
Okay, so that is correct. So now there are two more questions to ask. So one more question is, where is var1 itself? And then the second thing is, what is the size of var1? Okay? So what do you think is the address of var1? Is it the same as one of the previous items?
The topmost item.
Yep. So the address of var1 is the same as the address of var1.a because a is the very first member of the entire structure, which turns out to also be the beginning of the entire structure. So that makes perfect sense. What about the size of var1? In this case, 3 makes sense, right? Because we have 3 bytes here. The pointer is only a byte because we are talking about the toy processor. Okay. So I'll just kind of comment here, okay, and say that using TTP and TTP ASM, the address of var1 should be the same as the address of var1.a. The address of var1.b minus the address of var1.a should be 1 because it only has a size of 1, and so on. The size of var1 should be 3, and so on. Is that okay? Now, if you compile this code in an actual C compiler for the 64-bit platform, you're not going to see the size being 3. I guarantee it. It'll give you something that you would not expect. What do you guys think? What do you think is going to be the size of var1 when the structure is defined only with 3 different fields? We have one 8-bit number, a pointer to an 8-bit number, and then another 8-bit number. What do you think that structure is going to be in terms of size? And we're going to use a 64-bit architecture this time. Yes? Nope, it's going to be a lot bigger. It's going to be 24 bytes. Okay, the size of var1 is going to be 24 bytes. So, and I can see how you guys do not seem to believe that that's going to be the case. So we'll give it a try. Because, okay, so I'll explain it when we get there, okay? So the first thing is I'm going to convert this into an actual program first, and then we'll play with that in the debugger. Okay, and I just need like 1 or 2 assignment statements, so that this code doesn't get optimized out, because that's what the C compiler would do if I don't do something like that. So pound include stdint standard integer.h. Has anyone started to incorporate standard integer.h in your other programming classes? No. This is one of those things where it's actually useful for your other classes too. All right, so we'll go ahead and save this as struct.c in the temp folder. And then we'll go ahead and compile. Where's my big prompt? Nope. Uh-oh, I lost my big prompt. Yeah, that's okay. There we go. That's big enough. And warn all -o struct.c. Oh, forgot. Forgot a semicolon. That's what happens when you program in JavaScript and then get back to C. Because in JavaScript, the semicolon between statements is optional, and it says, but they prefer not to have that semicolon at the end of a statement. And you go back to C, that semicolon is not only optional, it is required. Yep.
If we were to compile the program as a 32-bit program on a 64-bit computer,
Mm-hmm.
then would it take up less space with back to 3?
Yes. So if you target 32-bit, then it will be back to a smaller one. Yep. Okay. So now we're back to the program. We put a breakpoint on line 24. Run the program. Okay. So now we'll take a look at a few things. So we take a look at var1.a, the address of. Okay. So for the most part, you just have to remember the last like 2 digits of the hexadecimal number. Okay. And then we want to print the address of var1, and you can see they are the same. Okay, so that part works. The beginning of a structure is the same as the beginning of the first member of the structure. That kind of makes sense. Okay, but now the question is, what is between the first and the second member? That should be only 1 byte. Okay, but that is actually not the case, because when we print the address of B, which is the second member of the entire, oops, not B, PTR, which is, it's off by 8 bytes. See how, the address of member A is ending with 80, and then the member PTR is ending with 88. So 88 minus 80 in base 16 or even base 10 is 8. So we're using 8 bytes to store 1 byte. That doesn't seem very efficient, okay? And then we look at B here, okay? This one is also 8 bytes away from the pointer itself, which kind of makes sense because when you're using a 64-bit architecture, every single address is 64-bit wide, because the address has nothing, the width of the address has nothing to do with the size of the thing that you're pointing to. Every single address is 64-bit wide. So that kind of makes sense. So now we want to look at the size of the entire thing, okay? Print, what is the size of the entire thing? So we look at var1, okay? Size of var1 is 24 bytes, just as I said. So it's been quite wasteful to store that 1 byte. Both member A and member B is using 8 bytes to store a 1 byte thing. So now the question is, why would the compiler do something like that? Well, first of all, what is 64-bit in terms of the number of bytes? How many bytes does it take to make up 64 bits? 8. Okay, very good. Do you think it's a coincidence that we're using 8 bytes to represent a one 8-bit thing? It is not a coincidence. So why do we want to do something like that? So now the question or the answer, okay? Let me switch to this screen here. So the next question is, what if we don't do something like that? What if we pack everything as tightly as we possibly can, okay? So if we pack everything as tightly as we can, I'm thinking about how to draw this thing because I need to have a consistent convention. So I'm going to use this representation here. Let's consider 1 square, as 1 byte. So if we pack it as much as we possibly can, then var1.a is going to take up 1 byte here. Okay, so we'll just kind of use this to represent 1 byte. And then var1.ptr is going to take up 8 bytes anyway, because we cannot make it any shorter. It's a 64-bit architecture. Every address is going to be 64-bit wide. So that's going to take up 1, 2, 3, 4, 5, 6, 7, 8 bytes. Okay. And then and then var1 dot b is going to take up 1 byte too. So the entire thing is only going to take up 8 bytes. I mean 10 bytes, which is a lot, quite a bit of saving. Okay. But now the question is, because this is a 64-bit architecture, how many memory access do I need to get PTR loaded into a register? We need 2, because every single memory access can only access things that are 8-byte aligned. Okay? So what that means is the first access is going to access 1, 2, 3, 4, 5, 6, 7, 8. So this is the first access. It can read 8 bytes at a time, but it can only read at the beginning of addresses that are divisible by 8. So that takes 1 read. Then you go like, oh, but that's only going to read 7 bytes out of the address. What about the last byte that we need to read? Well, that's going to have, we need another read operation to read that one. So that's why, if you do not, when you have things that are crossing the borderline between the 8-byte boundary, it decreases the efficiency of your program, because instead of needing only 1 read operation to read the entire address, now we need 2 read operations to read the entire address. It has to do with the width of the memory bus. With the 64-bit architecture, the memory bus itself is 64-bit wide. So even though from our programming perspective, it is still quote-unquote byte addressable, in terms of the hardware, it can only access 8-byte chunks starting at addresses that are divisible by 8. So it can read from location 0, location 8, location 16 in base 10, location 24, and so on. You cannot just say, oh, I want to read those 8 bytes starting at location 23. Doesn't work that way. So that is why everything is aligned to the 8-byte boundary whenever it's possible in the default mode of compiling. Now you can specify options to GCC to say, I want things to be packed as tightly as possible. Then it can give you something like this. It is actually possible, but this will not be efficient at all. So the question now is, are you going to sacrifice space for efficiency or the other way around? And most of the time, we have gobs and gobs of memory these days, so we would much rather sacrifice memory efficiency for runtime speed efficiency. So that's why we're not going to see the same thing as we would see on the toy processor. The toy processor has no such thing as reading only at 8-byte divisible boundaries, because it's a very simple architecture. So is that answering the question? Why everything is aligned to 8-byte boundaries? Yep, more or less. You still lost, or? Okay. Yeah, basically when things are not aligned, it will take 2 read operations, because 1 read operation will read a part of it, and then you need another read operation to read the other part of it. But when it is 8-byte aligned, then you only need 1 single read operation. All right. So is it still okay? All right. So back to the program that we have here. Okay. So yeah, go ahead. Hmm? If you divide, you mean subtract? Correct. Ah, okay, gotcha. Okay, so you are talking about. Okay, I'm gonna close this one because I used the command line to edit it. Okay. No. Okay. Okay, so you're talking about moving the A to be close to B, like that. Okay. The compiler will still spit out the same code, I think. Okay, but we'll find out. Okay. Um, so we want to compare the address of var1.b versus the address of var1.a. So this time they're only off by 1, correct. So the compiler does understand that you can pack things that are sequential, that are smaller, but things that are bigger, they want everything big that is big to be 8-byte aligned. So that's good observation. But you never know until you try it because it's compiler dependent. Very good. Okay, that's a very good question. Any other questions? No questions? All right. So if there are no questions, then we'll go to the assembly code. Okay, go back to, not assembly so at this point, but go back to the C code first. Nope, not that. Okay, where did I put that one? No. Am I using a different window? Nope. I think I just lost. Oh, I closed it myself. Okay, there we go. Okay. So now we want to look at this code here. And then we say, well, do we know how to do it in assembly? In other words, if I say, we want to change B to a 0, do we know how to do it in assembly? What do you guys think? Now this time we're talking about the TTP ASM, which means every single member is only 1 byte away from the previous one. Okay, so how do we do this in assembly code? So let's go ahead and look at the C code or the assembly code side by side to the C code here. So the first thing I would do is I would define the offsets, a few things, okay? So I would define x underscore PTR to be 0, okay? It's just a label, it's a symbolic name that simply means it's a 0. Then it will define x underscore B as a symbol to define where is member B relative to the beginning of a struct X, okay? So that's going to be x underscore PTR 1 plus, well, plus 1, right? And then what about A? So in this case, x underscore A, which is a label of where do I find member A relative to the beginning of a struct X. That's going to be x underscore B, which is the previous member, plus 1, because all of these members are only 1 byte large. Is that okay? And then I'll also define what is x underscore size. What is the size of a struct X? That's what this means. It is x underscore A, which is the last member of the entire structure, plus the size of that particular member, which is only of a size 1. Okay? All right, so with all of these things defined, let's check out how we can implement main here. The first thing we have to deal with is a local variable var1. Where do local variables go? On the stack, okay? All right, so when we write this, when we write this in assembly code, we still need the same thing as before, which is LDI D with 0 that initializes the stack pointer. And then we have main, okay, which is really just a marker to say that this is the beginning of main if main was a subroutine. So now we have to allocate for the local variable. And how do you think we should do this? The stack pointer is pointing to location 0 because it is 1 byte past the end. The stack is empty at this point. So I need to reserve enough room for struct x. How should I do that? Decremented by x underscore size. Very good. Okay. I know you knew what you were about to say, but you just could not find the name of the symbolic name. Okay, very good. So, but I cannot decrement that much. So I have to use an LDI to do that. So we do LDI. Cannot use D, so we'll put it into C. X underscore size. And then we do a subtraction. So we cannot avoid a subtraction this time. So we are subtracting C from D in this case. This is going to allocate space for var1. Is that okay? In other words, we are mixing something that we already knew before today's class, which is, oh, all local variables are allocated on the stack. And every time we want to allocate something on the stack, we need to decrease the stack pointer. We knew that before today's class. But now that we also know what a structure is, oh, if we have a local variable that is a structure, we just need to allocate enough bytes for the entire structure. Is that okay? All right. So that accomplishes the allocation here. So now the question is, so what do I do to put a 0 to member B of a local variable var1 that is a structure? How do I calculate the address? That becomes the question. So what do you think? What do you think we should do here? To basically do this line here, the only line in main that actually does something. So we know it has something to do with these label definitions, because otherwise I wouldn't put those things up there. So how about this? We put this into a register first, and then you tell me what we need to do with it. So we know the xb is one of the symbols that is going to be useful. xb as a symbol is defining the number of bytes between member B from the beginning of a struct x. Is that okay? Where is that struct x? Do we have a register pointing to the struct x at this point? Register D. Okay, very good. Because we just allocated it, right? We just allocated the local variable. So that means the stack pointer is pointing to the beginning of the entire structure. xb, on the other hand, tells me how many bytes is from the beginning of a structure to member B. So how do I calculate the address of member B itself? Just add those, right? Okay. So we'll say add CB, CD this time. So the key here is to understand why at this point C is the address of var1.b. Okay? Is that okay? Do we have any questions about this step? The stack pointer is pointing to the base of the entire structure that we call var1. X underscore B is a symbolic name that represents the number of bytes between the beginning of the entire structure to member B. Well, if we add those two, don't you think we will get to the address of member B of that structure? Maybe. Okay, so this is something that we can come back and revisit after Thursday, after the exam. But I'm just going to finish this code first. So we'll LDIA with a 0, STC0. So this means whatever. So basically, we're dereferencing the address of var1.b and then store a 0 to it. And as you already know, the address of and the reference they cancel out. So we basically end up storing a 0 to member B of the structure var1. This is something that I could not get to because of the lack of custom label definition. And now we can do it. I'm excited. We'll get back to this, okay? So don't worry if you don't get it today because it's a new topic. I do not yet have a module to talk about structures yet. I had stuff prepared, but for the x86 architecture, so it would not apply to the toy processor. So I kind of have to redo all that stuff for this. All right. So there's no new lab activity for today because I want you guys to have time to study for the exam on Thursday. You guys know that, right? Exam 2 is on Thursday? Okay. Okay, so if you have any questions, because of the studying or any material up to but excluding subroutines, you can ask me during the lab time. So that will give us plenty of time to answer those questions. All right, I'll see you guys over at the lab.